Hi there, this is the second video on Faraday's Law. This time we'll be exploring the mathematics of Faraday's Law. So let's begin by looking at the equation for Faraday's Law. Now recall that we have two different kinds of flux we have studied this semester. We studied electric flux, and we also have taken a brief look at magnetic flux, right? Magnetic flux is not really that different than electric flux, except for instead of electric field lines, you're using magnetic field lines. So remember that the definition for flux is the field times the area times the cosine of the angle between between them. So we'll label this one magnetic flux as the field strength, field density really. So that is the magnitude of our magnetic field times the area times the cosine of the angle between the direction of the magnetic field and the direction of the normal to the surface, to that area. So we have a surface. Remember that we must create a normal to that surface in order to have a direction associated with the area. And we can have a magnetic field that is, in the same way that we had electric fields, we can have a magnetic field that is directed at some angle with the surface, and it's penetrating the surface. So we're interested in, let's go ahead and put one more line there. We're interested in then the angle between the normal and the magnetic field direction, right? Remember, this is what is represented by that theta. The same concept as the electric field flux, right? We're just exploring this using magnetic field this time. The reason that this is important is because we'll go ahead and write out this equation. We're interested in, remember the EMF, we use this from a battery, right? In other words, it's the maximum voltage that is possible to generate. Remember, we use this in the case of perfect batteries in Unit 2. We're now going to use it as a non-battery situation. It still stands for the perfect voltage that can be generated, okay? But in this case, we're actually talking about a voltage that is generated around the entire hoop, okay? So this is going to be given as negative. Now the reason it's negative is because in the last video we explored the notion of Lenz's law and that it was an oppositional phenomenon. In other words, it's always going to oppose change, and that's what that negative sign represents. We're not that interested in using that negative sign in our calculations, since we will just use our first video and our right-hand rule to determine directionality. But I wanted you to know why that negative sign exists and why it's on your equation sheet. This N represents the number of hoops, so you can actually have more than one. If you keep doing that, you end up with a solenoid. And then we're interested in the change in magnetic flux in time. And that's why it's so important for you to understand flux. That's why I wanted to introduce it sooner. But now that you have a concept of what flux is, that's like a damaged Cheerio lifting weights. Now you know what the flux is, then understanding this equation is not that far of a reach, okay? So flux, not that bad. Change in flux, that's the tricky part. That's the thing that we have to be a little bit cautious about. Remember that this delta here is very, very important. Very, very important. Okay, so let's look at the case where we have this situation and we had a magnetic field initially that with a strength of 0.25 Tesla, and then we diminished that field to a mere 0.1. How long did that take? Let's say that it took, let's say, 1/10 of a second. Okay. Now let's look at the dimensions of our hoop. If we want to look at how long the hoop is, we can give ourselves an 80 centimeter hoop, and then along this dimension we can give ourselves a 50 centimeter width, right? Then what we're interested in is the voltage that is actually generated around the hoop and the magnitude of the voltage that is generated around the hoop. So let's go ahead and calculate that magnitude in this particular instance. The first thing we need to do, I put the magnitude so I don't need to concern myself with that negative sign. I just want to know what the magnitude is. Oh, I forgot to give you theta. My apologies. So theta will be then, in this case, let's make that 55 degrees. We want 55 degrees from the normal to the direction of the magnetic field. Okay. Now, N in this case represents the number of hoops in every case for this equation. Now, since I haven't stacked a bunch of windings around this, we really only have one, and under most circumstances you will have one in our problems that we are discussing in this class. So you can almost always just put that negative in as just nothing, just one. Okay, now the change in flux is what we're interested in now. And the change in flux is going to be the final flux minus the initial flux. So you can go ahead and write that out. Final flux minus initial flux, in the amount of time that it took for that change in flux to happen. Now hopefully this reminds you of our first video. It isn't necessarily the flux itself that's the problem, it's the fact that it is changing in time that's the problem. The faster it happens in time, the stronger the induced effect. So, what is our final flux? Well, it's going to be B final, A final, cosine, theta final, and then we're going to subtract B initial, A initial, cosine, theta initial. Now you may notice that in this we have not really changed all of these things. So theta final and theta initial, area final and area initial are all unchanged. They're all the same. So we can actually pull those out. It makes it simpler. We can say this is the change in B field times the area always times the cosine of always theta, because we haven't changed our angle at all and we haven't changed area at all. All I've really done here is use the distributive property in reverse to pull A out and cosine theta out, since those A's and cosine and thetas are the same. So that's just a handy way to start your problem to make sure you're not having to write everything out. However, if you like this format, then by all means stick with it. There's nothing wrong with that format. Now, the final was 0.1 Tesla and the initial was 0.25 Tesla. Area is going to be 0.8 meters times 0.5 meters, and we have cosine of 55 degrees. All of that is divided by 0.1 seconds. Now make sure you're in degrees here, because you're reporting your cosine as degrees, so you'll need to make sure that you're in degree mode here. And notice that we end up with a negative answer, and that's not important because we're taking the absolute value. It could have been B initial minus B final in that case. Remember, we'll be using our right-hand rule and Lenz's law to determine the directionality of the current, and we can do that also very easily in this video. So I get 30, whoops, no, 0.344 volts. This is completely reasonable. With such a large hoop and such a strong magnetic field, it's totally possible to get this kind of voltage that would actually induce quite a strong current in our hoop, since the resistance of our hoop is probably pretty small. Okay, so this is the voltage that we would work with. If you have a resistance that's available to you in your hoop, you can actually use that in the same way that we use Ohm's law. So you would just use, in other words, if you have a resistance, all you have to do is apply Ohm's law in this way, and it works out fine. Okay, so what about the direction? Well, from our first video, remember, if you're this hoop, and this is the magnetic field, and it's going from strong to weak, then what you're going to do is, the first question you ask is it going, basically, is it going up through the hoop, or is it going down through the hoop? And it is basically going up. Yes, it's to the side a little bit, but their component of your field is going along this, not anti-parallel to it. So you got mostly flux from bottom to top of this hoop. Okay, is it decreasing or increasing? It's decreasing from 0.25 down to 0.1. So if we have a field up and it's fading, then you as the hoop are going to try to do your best to increase the flux in the upward direction, and in order to do that you will need to establish a current going this way through your hoop. So we know the direction of the current. If we know the resistance, we can also determine then the amount of current. We did not determine the resistance in this problem, so we cannot calculate the current, but we did calculate the EMF, or the induced voltage, about this hoop. Now, one of the things that you'll notice about Faraday's law and flux in general is that it depends upon three different things with flux, and it also depends on the number of windings, and it also depends on time, right? So in particular, in the denominator, it depends on how quickly something is happening, and in the numerator it depends on three things. It depends on the strength of the field, it depends on the area through which the flux is going, and it depends on the angle. So if I have a hoop here, and the way that I've drawn this hoop, I've tried to make it clear that the right side here is the front, it's very close to you, and then the left side here is in the back, farther away. And I expose the hoop to a magnetic field, like so. Then there's an interesting effect that occurs when I twist the hoop. So if I turn this hoop, then you can see that what's going to occur with the magnetic field is that I'm actually going to be incorporating fewer and fewer magnetic field lines. So let's take a look at the normal to the surface here. Whoops. So normal to the surface here. Since the magnetic fields lines are going that way, I'll go ahead and draw my normal on that side. And if we tilt our hoop, then you can see that the angle between the normal to the hoop is changing with respect to the magnetic field. And remember, it's that angle that gives us our flux, right? As we change all the way to here, then we get zero flux, right? So what we could do is talk about this in terms of not only the strength of the field and the area of the hoop, but also the cosine of the angle between its normal and the magnetic field. Now, this is not a linear process, so it's not as easy to calculate a constant EMF that occurs during a rotation like this, because it's not a constant EMF in general. It's in fact sinusoidal. So instead, we tend to talk about these kinds of turns, like you will have most likely in your homework, as an average induced EMF, because we're going to actually have a little bit of induced EMF as it starts to tilt down, and then the more it tilts down, the more rapidly EMF is produced. So just wanted you to be aware that that is another way that this can change. In this case, the EMF that's induced would be the N is still the same, so we keep that out front. The B field is still the same, so keep that out front. The area of the hoop hasn't changed, that's still pi r squared. The only difference in this case would be cosine of our final theta minus cosine of our original theta. So the same thing, we're able to separate out everything in our equation that stays constant and only take the difference of the things that change. This is very similar to what we did in the previous one. Now again, this is going to be an average EMF. It's always an average EMF, but under linear circumstances it actually equals the EMF the entire time. It's very similar average velocity or other average rates. Okay, if we want to, we can talk about the resistance as well. Now this may give you a sense of why it's a really terrible idea to have metals in MRIs. Even if they're not magnetic metals, it can still cause quite a bit of trouble. If we have a small metal hoop, so we'll think about it in terms of an MRI, okay? You just have some small metal hoop here on this hoop, but the area, let's put it at, well, let's say a couple of square centimeters, shall we? 2.5 square centimeters. Remember that that is equal to 0.00025 square meters, right? So it's quite small. And also we're going to use typical magnetic fields for an MRI machine, which can, a reasonable magnetic field for an MRI machine is around 5 Tesla these days. That's actually a pretty gentle MRI these days. At 5 Tesla, what happens in an MRI machine is that it pulses the magnetic field. So it'll pulse like this, and it waits for everything to restore. So if you're interested in in MRIs as one of the pre-med students, then essentially the way that this operates is that a lot of the atoms will try to align with the magnetic field, and then they will decay their alignment over time, and that decay gives different decays for different atoms. So it allows you to differentiate between different things in a spatial way. Okay, so what we're interested in this case is actually this delta t, which is on the order of less than a millisecond. We're talking about something like let's say about 0.3 milliseconds, something like that. That might even be a little bit long, but let's just be modest with it. So if we choose to have that our change occurs from 5 Tesla all the way down to 0 Tesla, it's going to occur in 0.3 milliseconds. We would write that as 0.0003 seconds. Then we can easily, if we know the resistance of this ring, and we'll put our resistance as, let's give it a very reasonable resistance of about 0.0005 ohms. That's actually rather resistive. It's much more resistive than a copper ring would be. Now what we can do is determine what the current is in this tiny hoop if you accidentally brought it into an MRI machine. So first of all, we would find the magnitude of the EMF, and that would give us, this is one ring, so n equals 1. We're not interested in that. We want the change in the flux upstairs. So again, let's pull out everything that stays the same. The area of the hoop stays the same. Cosine theta stays the same. And in this case, what we'll do is we'll say, in fact, that we get the maximum flux through the hoop. It might not be maximum flux, but all you have to do is point it through the hoop and you get maximum flux. And the only thing that changes is the B field, where we have 0 Tesla minus 5 Tesla. And then the amount of time is 0.0003 seconds. So remember, our area is given as 0.00025. Let's go ahead and calculate that. And I get 4.17 volts. Now we can establish the current by using Ohm's law. Now this is not going to be exactly realistic, because in fact this would produce another effect that we haven't studied yet that would make it where the ring is going to actually move around and try to prevent this current from forming. But let's go ahead and if you forced the ring to stay still, if you force it to stay still, and we'll calculate the amount of current that goes through this ring. It is then given by Ohm's law, which would be 4.17 volts divided by, where's our resistance? 0.0005 ohms, which gives us 8,000. It's about 8,000 amps. It's not exactly 8,000, that's just one significant figure, but like I said, the effect is in reality would be highly disturbed by the motion of the ring at that point. So if you were able to hold it still, you would probably get something around 8,000 amps. You would melt the ring, in other words. So this is why it's one of the reasons that it's highly inadvisable to bring metals into an MRI. It is possible to get out of one without getting injured, but it's not a good idea. So, okay, this hopefully explains the idea behind Faraday's law. There's many applications for it. So, again, if you guys have questions, let me know, and I can maybe pile in any videos that are extra to let you know about any confusions that arise in the class. If I keep getting, frequently asked questions, then I might make a FAQ video for the class. So, okay, next video we're going to be talking about something called motional EMF, which is really what happens to this ring in reality.